Alrighty guys, what's up? Daddy here again this evening. And in today's video, we're going to be jumping into a topic I promised for a while now, and that is benchmarking different GPU and CPU performance regarding a lot of the open source LLMs. So in a video prior to this, I basically went over an add-on to the BenchDaddy GPU benchmarking suite that I've been working on, and I updated it so that it can test at scale. A lot of the different Ollama flavors, or basically anything that's in the Ollama library, is now testable with a wide range of GPUs and the CPU. So, if you're interested in the actual code or you want to run this for yourself, the link will be in the video description, not only to the GitHub, but also to the video where you can find the code and you can find all that stuff more in depth. But basically, that's it will form the basis of this discussion today, and I'll link the underlying spreadsheet. Sorry, let me just go pull it up really quick. But I'll link the underlying spreadsheet as well, so you guys can go check that out if you're interested and you prefer data in the more raw form. But for today, I'm pretty much just going to go through and go through over this Looker Studio presentation I put together. I think this is a great tool. I used it in the past for the last kind of comparison with the basic test in the GPU suite, and I think it's a very underrated data visualization tool, so I highly recommend Looker Studio. But in any case, we'll go ahead and hop into it today. And I'm going to go ahead and put this in presentation mode. I'm going to need to jump around a little bit some of these links just to explain things. But for now, I'll go ahead and put it in presentation mode so we can see this a little bit better. And the first thing I want to do, or I want to talk about, is I want to explain the hardware environment, and then I'll talk about the GPUs I used in the study as well. And I think it's important to understand the context. So, and then I'll try to explain why I did these things as well. But so there's three different hardware environments, and basically the first is my Supermicro 4028 GR-TRT server, and that is what we're looking at here in the first category. The second one is my desktop computer, pretty much, and I'll go over the specs here in a second. And then the third one is I have a Mac M1, and I've always heard so much about Macs being really good with or really good for Llama CPP that I wanted to try it out, especially since Ollama is pretty much just a wrapper around Llama CPP anyway. So I figured that we could do not only a GPU comparison but also a CPU comparison, and I'm going to try to put all that in the same video. So do bear with me; it is a little bit long, but I'll try to get through the information as quickly and as efficiently as I can. So we'll start here. The specs, just to be explicit, for the Supermicro server, we have Xeon E5-2699 version 4. That's the CPU. The longer name is here. Manufacturer is Intel. Has a base clock of 2.2 gigahertz. Each core or each CPU has 22 physical cores, and then there are 2 CPU sockets. So there's 2 different CPUs in this particular machine, and that's 88 threads or 88 logical cores in this case. I also wanted to include, for just completeness, the underlying OS. So this is the bare metal. This is the OS that's actually loaded onto the machine, and then I ran everything in Docker. So that's why you see the bare metal OS, and then you see the Docker, or you see OS as Ubuntu 2204 with Docker, just letting you know that that's the OS loaded inside the Docker container where the actual model itself is running. So, and I just wanted to make sure that you could kind of easily tell, what the underlying OS is and what the Docker OS is, and that way maybe you could make your own assumptions about what the performance, what that might do to the performance. I know some people will say that it's better to do this kind of thing in bare metal, but using Docker is extremely convenient, and from my experience, like the performance degradation is only marginal. So I think this is kind of a a fine thing, especially if you're keeping things consistent across all of your tests. But for you at home, maybe you have different applications, so do keep this in mind. The next thing is we have DDR4 RAM, Hynix or Hynix. I'm not sure how you pronounce that, to be honest with you. That's manufacturer. The memory frequency, and this is what it's actually utilizing, not what the capacity is 1866 megatransfers a second. The RAM size is just over 1.5 terabytes. The motherboard is a Supermicro X10 DRG -O plus CPU. So that's basically just that there are different motherboard configurations depending on like how many GPUs you want, or like what kind of GPU configuration you want for the server. And this is the one that just has eight vertically installed or vertically situated GPUs in the back of the server. And then the interconnect technology is PCIe 3. So, and there's probably some other things I'm missing, but these are the most relevant hardware environment attributes that I thought to add. So the next is my desktop machine, and that is a Ryzen 9 5950X. So pretty performant there. Probably more than I need for my desktop, to be honest. But so this is an AMD CPU. Its clock is significantly higher, or its base clock is significantly higher at 3.4 gigahertz a second. There's 16 physical cores, only one CPU in this case, 32 logical cores or 32 threads. I'm running Windows 11 on the underlying machine itself, and then I'm running Ubuntu 22.04 Docker again. So just another nice difference there. This is a DDR4. This time it's Corsair, has a much higher memory frequency, and the RAM is significantly smaller. And then the motherboard is this MSI B550M Pro VDH motherboard. And it's actually part of another build I've done in the past. So if you're interested, you can check out that and some of my earlier videos. And then this PCIe 4.0. So it has a faster PCIe. So in theory, it should be able to transfer data a bit faster in this case. And then we'll see if that actually comes into play and when we get the results. And then finally, there's the Mac M1. I just wanted to do a comparison for on Apple Silicon. I know that the M1 is kind of old at this point now that we have the M3 Pro Max, what have you, coming out. So this may not be as relevant, but I wanted to still include it as a comparison because of the unified memory. So anyway, it's Apple, obviously. The base clock is pretty comparable to what I have in my desktop. There's 8 less physical cores, and only one CPU. And interestingly enough, only with Apple these are actually P cores and E cores from what I remember, and they only have one thread per core actually. So that was an interesting different architectural difference I didn't realize. And OS in this case is Sonoma, so version 14.6.1, and then again using Docker, so underlying OS doesn't matter as much. The RAM type is LP, or low power DDR4, so a little bit different RAM setup. And then this is the Hynix is the RAM manufacturer, and then the RAM frequency is quite a bit higher at 4466. And then finally, all of this is kind of integrated system on a chip from Apple, so there really isn't a traditional motherboard, so to speak. It's just kind of all built and soldered together, and the same thing kind of with the interconnect technology at this point. So that's what we're looking at in terms of hardware. And the next thing that's relevant is the GPU specs, or what GPUs we're actually using. And if you've been watching my channel for any length of time, you kind of probably already know this. It's the P40, the P100, and the RTX 3090. I'm hoping to add the Titan to this list of GPUs pretty soon. And then I'll try to start including some other ones as well, as I have basically the money to to build them in. But anyway, so this is compute compatibility. This is the specific basically version, if you will, of each GPU. So for example, certain GPUs have different iterations or different releases, and they have different computational abilities actually. So this one is just letting you know more specifically what version or what P40 it is you're actually talking about in this case. So this is 6.1, 6, 8.6, and these are the prices. So this is not the price I paid at the time that I got it. This is the price whenever I was creating this last week. This is basically the price that you could pay on eBay for a either a refurbed or new or whatever the whatever was available at that particular time. And basically what this means to me is this is the price you can pay from a reliable seller. So somebody that has like a clear business or a clear trend that they are a reliable seller. They have like good feedback, above like 95% satisfactory in the deals that they have or in the transactions they've already made. And they've had like a couple hundred transactions. So that's the kind of thing I'm looking for when I'm saying these are reputable sellers. So places that I would actually buy the GPUs from. So I'm trying to be as realistic as possible in terms of what these prices actually are. And then obviously I choose the lowest one of all of those sellers that I can find. Obviously the VRAM size. So we have 24 for the P40, 16 gigs of RAM for the P100, and 24 for the RTX 3090. Different actual VRAM types. So GDDR5, HBM2, and then GDDR6X. So all different architectures there for the different GPUs. Quite a bit of difference in terms of bandwidth as well. So we have P40 with the lowest bandwidth. We have the P100 with about twice the bandwidth of the P40, and then the 3900 with the absolute highest bandwidth. So, and we'll see if this makes a difference later when we're looking at the results. Excuse me, I just had a coughing fit out. Still getting over a little cold. Here we have the TDP, or basically the top wattage, or basically the most wattage usage you can expect from these GPUs. So 250 and 250 for both the P40 and P100, and then the RTX 3090 is 350. NVLink, this could be relevant, and in fact, I would argue that it probably is based on the results you'll see later. These two do not have NVLink. The RTX 3090 does. And just as a side note, I found this interesting. A lot of people have asked me, about NVLink for these two GPUs over the, course of the time I've been doing YouTube. And I don't think that, at least that I've found, there is any, like for the PCIe versions of these GPUs, I don't think that there is a NVLink option. Now, if you buy the SMX2 form factor, so the ones that actually sit, that are like square and have the square heat sinks and look kind of like more traditional chips, like those that with that architecture and form factor, those actually do, or I guess by nature, support NVLink. So if you do see these GPUs listed as having NVLink available, it's, from my understanding, only for those SMX2 form factor GPUs. So just wanted to clear that up. I know that this is something only probably a few people will get, but just thought I'd mention that while I had it in mind. Next, just looking at the theoretical performance. So, what we should expect, or how, better put, how these GPUs should stack up based on what theoretically we should expect. The P40, in terms of FP16 performance is basically negligible. And so basically the P40 has very good single precision or FP32 performance, but it performs pretty badly in terms of half precision or FP16, and then double precision or FP64. So in both those cases, it supposedly has poor performance and really only operates well for the FP32 case. And traditionally, this is more of a GPU thought of for inference, although I would argue that's not necessarily true. The P100, it is kind of a more generic GPU, and in fact, it's the only GPU that has really good or I should say relatively decent double precision here, but slightly worse on single precision, but it handles the half precision or single precision cases, half precision cases much better. And then you have RTX, the RTX 3090, and you have basically same performance and far and away the best performance in terms of half precision, single precision, and then it pretty much, I would say, almost is the same as the P40 in terms of double. But this is really not that relevant for AI and machine learning, to be honest with you. I mean, in scientific computing, it's still relevant in some cases, but for the most part, these are going to be 32, 16, and these days even quantized, especially with LLMs, quantization is huge to kind of reduce that that tensor size as small as possible. So, okay. So now we've got those out of the way. That's the hardware environments and then the GPUs that we're actually going to be looking at in this study. And then the next most pertinent thing is the prompts. So I wanted to kind of come up with a well-rounded prompt suite. And the idea initially was to create 5 prompts that increased in difficulty. So prompt 1 would be the easiest, and then 2, and then 3, and then 4, and 5 would be the most difficult. Although I think in practice that didn't really come out that way. And I think I probably could have done a little bit better job of the response format in terms of like asking them to format things differently, or I could have maybe done a little better job there. But overall, I think this provides a pretty good, well-rounded list of prompts that ask for different things and encourage different outputs from these various models. So I'll go ahead and just go through these quickly. The first one is obviously the most simple. It just says explain what artificial intelligence is. And this is just a generic thing that would require relatively few tokens from whatever model that it's asked to. The next is describe the process of photosynthesis in plants and how it supports the ecosystem by producing oxygen and glucose. So, a little bit more complicated of a question, and hopefully elicits a more complicated response from the model. The next is provide a detailed explanation of quantum entanglement, covering the EPR paradox, Bell's theorem, and how entanglement is utilized in quantum computing for teleportation of information. So, more complex topic requires, in theory, more logic and reasoning, and the response should probably be longer. At least that's what the idea is. So, continuing on with that idea, the next is write a short story about a scientist who discovers a new form of energy, but must face ethical dilemmas as governments and corporations fight over control of the technology. The story should include elements of suspense, character development, moral conflict. So not only is there a pretty high level of logic here and understanding that has to go into it, it's asking for a more of creative side. And depending on whether it's an instructor, whether it's a different model, it may do better at this particular task. So this is designed to not only have a longer prompt response, but also take things in a more creative direction. And then finally, the last is list and explain the top 10 most important most important breakthroughs in artificial intelligence in the last decade, focusing on both advancements in hardware and algorithms. So this is, since it says list the top 10, it's probably going to have a bulleted response or some sort of, hierarchical response. So Again, testing the GPU in just a little bit different way, even if it's probably overall maybe a more simple prompt. So that's really the key here. And if you wanted to go back and test these with different prompts, like the benchmark and the suite is made so that you can easily integrate new prompts. In fact, there's just a YAML file there. All you have to do is just delete the ones you don't like, add ones that you do. It's pretty straightforward, and you could test hundreds if you wanted. So that's all there and available on GitHub for you if you'd like to do that, or you don't like the prompts that you see here. Okay, next, it's worth mentioning the test runs. This is kind of the experimental setup here. All tests were performed by averaging the test metrics across each prompt for each model and GPU combination. So basically, you have, the way that it works is you have a model and GPU combination, and a Docker instance is instantiated for that, and that model is loaded onto the Docker container, or at least depending on what you said, it could be a volume or it could be the container itself, whichever of those. And the container only has access to the GPUs that you set in the config. So if you want to test one GPU, you can set that GPU ID in the config, and then that model or list of models will be tested against that GPU. So basically, you're testing model and GPU combination. And then for that, each prompt is tested. And then each prompt is tested a number of times so you can get an average. So for example, you can set test runs as 3, as 5, as 10, as however many you want, and then it's going to average that across all of the runs for each prompt. So you can get an idea of, basically for this prompt, for this model, and this GPU combination, how did the model perform? And that's essentially the goal here. So the GPU test one, I kind of broke this into a number of subtests, or a number of smaller tests, so it was a little easier to handle. But GPU test one, and this is the hardware environment one, so the Supermicro server where all of my GPUs are. So basically hardware one is going to be where all the GPU tests are occurring, because that's just where I have them right now. And then the prompts, this is listing the number of prompts that, or I guess all the prompts were tested. In this case, it's the same for all of them, all 5. And then the models for each test. So in this case, for test 1, it's the 8 billion instruct 4-bit quantization, 8 billion instruct 8-bit quantization, and then 8 billion instruct the full half precision here. And then tested with 1 RTX, 1 P40, and 1 P100. So just testing each of the single GPUs with all of the models that will actually fit inside of the GPU. And that's another thing you may be asking, well, why didn't you just test all of them? Well, I wanted to test a good smattering of models that would actually fit all the way inside of the GPU VRAM. So because I don't think it's a fair test to try to split between the CPU and GPU, which Ollama will do, but I don't think that's truly testing the performance of the GPU at that point. So that's why I kind of set this test up that way. The next test, it kind of follows a similar narrative here. So the hardware environment one, we're still going to use same prompts, same basic models, but now this time we're testing 2 GPUs so we can load more intense models, larger models onto both GPUs and kind of split across both GPUs here. So we've included the 70 billion instruct 2-bit quantized K. And so K and S and KS and KM, these are all ways of keeping things quantized, but including more information. And I should probably have done a little more research here, to be honest, but there is a good bit of research here in this area, and maybe I'll make another video following up here. But basically, my understanding is these are ways to keep more information at the 2-bit quantized level. So kind of intermediary steps between like this perhaps and the like baseline Q3. So it just kind of gives you different, like a little bit better performance without having to go all the way up to the next full bit of quantization. So from Q2 to Q3 or Q4 or something like that. So, and in the comments, actually, it was kind of, I just did a little preliminary research, but at this point I've kind of forgotten it. If you know, please drop it in the comments and let me know what these actually stand for. Or if you can link me to some papers or something with a good explanation, I think that'd be awesome. But honestly, for our purposes, I don't think it really matters that much. We're just trying to get an overall idea of how these GPUs work with different models. So I tried to include some of these odd ones that I don't understand that well, so that the test can be as comprehensive as possible. So anyway, we have a 26 gig one, a 31 gig one, and a 43 gig one. And so we have the 70 billion, the Q2, Q3, and Q4. And I only had 48 to work with, and I couldn't go up to the next model size. So that was as big as we could go with the 2 GPU setups. So that was test 2. So test 1 is the one GPU, and test 2 is 2 GPUs. So it kind of makes a little bit of sense. And then test 3, we have, again, on hardware environment 1, same prompts. But this time, this is all of the models. So notice there's a comma here. So this is 2 GPUs, and then 2 P40s, and then 2 P100s. This is all of them at once. And what I wanted to do here is just see how having different models would work. So for example, like, where's the bottleneck? Is there a bottleneck between the P40, P100, and RTX 3090? Do they play nicely together? Can you even run this kind of setup? So all these other this is kind of an experimental setup to understand, how performance looks when you're having a mismatch of GPUs and you're splitting across so many. So just wanted to kind of test it and see how it would go. And another thing here to note is that I went all the way up so that the model doesn't fit all the GPUs. So in this last case, so we're using fully utilizing all 6 GPUs, and we're also pushing some of it onto CPU RAM. So this should cover all of the cases to see how does performance look when you have that scenario as well. Okay, and then so those are the first 3 tests. The first 3, or I guess I should say 3 GPU tests, and then we also had 3 CPU tests. So this is just testing each of the hardware environments independently. So no GPUs anymore, just the same 5 prompts. And then for hardware environment 1, so this would be the Supermicro server. We tested the 8 billion instruct 4-bit quantized model, and then the 8-bit quantized model, and then the half precision 8 billion model as well. And you may be thinking, okay, well, you didn't really test that many models for the CPU, like why not? And you'll see later in the results, like the tokens per second was just so low. I didn't think it was really worth my time to continue testing larger models, because I think at this one we were already looking at like 3 tokens a second, which is so slow it's, in my opinion, unusable. So I was trying to gauge performance without just kind of wasting time. So I think beyond that, you kind of would have asymptotically approached like 1 or 2 tokens a second. So anyway, let's see. Test 2 is hardware environment 2. So this was I believe it was my desktop setup. Let's go back one more. Yeah, desktop setup. So yeah, this is the desktop setup. And again, I only tested 2 models because after this one, it was so slow that it was, I don't think diminishing returns at that point. And then test 3, same thing. This is on the Mac. I was actually quite surprised. I thought the performance would be surprisingly good here. It was actually probably the worst overall, which is, I know it is the M1, and I only had, I think, 16 gigs of unified memory, which isn't much, but I expected performance to be better. especially as much as people are bragging on Apple Silicon for machine learning. So I'm not a hater. I like I like Apple products a lot. I think they always do a good job, and it may just be the fact that I have a old laptop, so M1's kind of old now, and maybe that's why the performance was less than expected. But in any case, that's the experimental setup. And now we'll look at the test metrics, and I do apologize. Now we're 30 minutes in, and I'm still describing the setup, so I'll try to make sure that in the video description there's a link just to go straight to the results if you don't care about any of this stuff. And I'll try to insert something in the beginning of the video to let you guys know, because I know some people just really don't care. They just want to see the results, and that's fine. But the test metrics that we're looking at here, the load duration. So how long does it actually take to load the model onto the GPU or into the CPU RAM or whatever the case is. Prompt evaluation. So how long does it actually take to process the input prompt? And then response evaluation is how long does the model actually spend generating the response? And then total duration is just 1 + 2 + 3 from above. So the summation of all of this. And then one thing I forgot to add here is there's also a little bit of overhead. So the time may not match exactly the summation of the load, the prompt, and the response time. So just if it doesn't match, then there's a little bit of overhead. So sometimes it may not match quite exactly. But tokens per second is generated by calculating, by dividing the total number of tokens. So basically the tokens generated in this response duration by the duration itself. And these are actually output in nanoseconds. So they're multiplied by 10 to the 9 and then divided, or basically they are divided and then multiplied by 10 to the 9 and put them in seconds form. But in any case, you guys get the idea. And then I took this exactly from Ollama's documentation. So that's how they recommended to do it. And these are actually all of their metrics that the model already outputs. I'm just basically made it into a scalable testing solution, and then I'm providing all of this analysis. So I'm not, not reinventing the wheel or anything here. I'm just trying to make this digestible. Next thing is at the end, I tried to do a quality analysis. Now it's naive at best, but I wanted to look at, so there is the model score. So this is the Hugging Face Open LLM leaderboard. And this is the average score for a particular model. And if you want, you can go take a look at this, and I'll explain it later when it's more relevant, so it's fresher on your mind when we're looking at it. And then they do the same thing here with the LLM. It should be Arena. Sorry, but there is a Arena score in the chatbot Arena LLM leaderboard, and this is basically like a head-to-head competition between LLMs that you can actually go and do kind of like a pairwise comparison, like is model A better than model B? And it's like a voting system, and they actually have a leaderboard based on that. So I feel like that's kind of relevant because that's user input or user driven. What model is best? It's not benchmark driven. So I think both of these metrics are good for different reasons. So anyway, these are all the things that I use to try to evaluate and explain the results. The next thing is the overall macro level of view. So I tried to keep things as large as possible, and then we'll kind of get granular after this, and then we'll look at the quality. So sorry about that, guys. I'm coughing again. So what I'm going to do here is I'm going to explain this chart, and there are a couple of subcases that I think are interesting to look at, and I'm going to explain this chart. So I guess the first and foremost way that we should assess these GPUs, or I think that these should be assessed, is just looking at raw performance. And performance, the two most important metrics in my mind are the tokens per second and then the total duration. So how much token generation are you getting scaled? And then how long is it actually taking for this to happen? So it shouldn't be a surprise to anybody that the RTX 3090, and this is holistically, by the way, and we'll look at some other cases as well, but holistically speaking, the 3090 outperforms. So it's has over double the token generation as the P100. The P100 just barely beats the P40. And then the CPU cases are significantly less. And then, as you can imagine, the case with all the GPUs, this is all the GPUs, this is the worst case scenario. Not only because the GPUs are mismatched and you have different bandwidths and all this other kind of stuff going on, you have to transfer it through more GPUs, but also because there's one case in here where the models can't fit all the way on the GPUs. They have to use the CPU RAM as well. So that, I'm sure, has dragged this average down significantly as well. So just wanted to highlight that. And then another thing that's of note here is that these so RTX 3090, this is the single GPU case and the double GPU case. So the average of all of those over all the prompts, all the models, all the combinations, etc., for both of these cases. So pretty good overview here if you just want a really top level view. But I'm going to throw in some caveats here. The first one is, while I was actually doing this, I realized that in one of the cases, one of the models failed and has 0 values. So for the sake of removing outliers, we're going to take that out of the equation, and I think it's the K3_K_S, this guy right here. So if we take that away, the picture looks a lot more normal. And this is kind of a lot more what I expected. Because in the other one, you notice that the time curve went up, even though the tokens per second generation was flat, or almost flat, with the P40 in that case. But anyway, so when you remove that outlier, you can see a lot more clearly what the things should look like. And the P40 does do a better job overall from my empirical testing than the P100 actually, which is surprising because the theoretical specs say that it should probably do a little bit better, especially for the LLM cases, because it has better half precision. So, just another reason why I don't think you can take theoretical specs or non-tested specs, with any kind of certainty, because these results that I'm showing don't match what we should be seeing if the theoretical specs were true. So, and of course, it could be that I'm doing something wrong. It could be that there's something weird in my setup. So there's always other things, but this is my second set of tests now, and it seems to kind of say the same thing. So I don't know that that's the case. Anyway, so okay, now we've taken out the outlier, and now let's look at some other interesting cases. So let's look at only one GPU. So we'll deselect that. So what we find here is that in the one GPU case, there's actually like the performance gap between the 3090 and the P40 increases quite a bit. And also the performance gap between the P40 and the P100 increases quite a bit. So, it's interesting that in the one GPU case, I mean, it's not interesting, it's actually, I kind of makes sense that when everything's happening on one GPU, there's no data transfer. The raw power of the 3090 is actually able to, even more outperform some of the older GPUs. And then now if we look at just the 2 and 1, we notice that we're pretty much flat here. Just some slight improvement of the P40 and the P100, but not a whole lot. And there's also another huge gap from these cases as well. So I guess overall, doesn't really matter how much you slice it, at least as far as this is concerned, whether it's 2 GPUs or 1 GPU, the RTX 3090 significantly outperforms the P40. But if you're talking about P40 versus P100, then the bandwidth differences the bandwidth can really make a difference between those 2 GPUs from the 1 to 2 GPU case. And another caveat here is the fact that the 3090s have NVLink. So if they didn't, then you might see this be lower for these two cases, but that's not something I've explicitly tested. That's something that is on my list of things to do. I just haven't explicitly tested the NVLink to show, exactly what kind of performance gains you get with it versus without it. Okay. The next thing here, and let me just reset everything back to normal. We'll keep this because that's outlying data anyway. So, okay. If we're taking it, so if we're moving to price per token, or price per token per second rather, and keeping things holistic, this is probably the most important metric. And I wanted to go over it second because I think that a lot of people just care about the performance. So I wanted to give people that want that performance summary, what they want first. But I do think that the price per token per second is probably the most important metric because objectively, yeah, the 3090 is the best in terms of performance. And you can see that, and that's pretty obvious. But not in every case is it the best in terms of price per performance. So what you're actually paying for that performance. So overall, it is still better than the P100, significantly better than the P40, significantly better than the P100, and then way better than all of the GPUs put together. And of course, this is expected. They're mismatched GPUs. The price is a ton for the performance. And I also tested one case where, like I said, the models are loading on the CPU RAM as well, which inherently slows things down. So I don't feel like this is a relevant data point either. I just wanted to kind of put this in here to show you how drastically different things can be when you are using tons of CPUs that are mismatched, and then also using GPUs and the CPU as well. The performance really goes down and the price goes up. Now that said, this does allow you to run models that you wouldn't be able to run otherwise, just in terms of VRAM and loading larger models. So if you have GPUs available and you want to run the models, then sometimes this makes sense even if the performance is bad. So just wanted to highlight that as well. But for now, we'll take that out. So I'll take the 6. And we'll just look at the P100, P40, and the 3090 in a much nicer graph there. Okay, so now let's look at the 1 GPU and 2 GPU cases. And this is where I was saying that in some cases it's better, some cases it's not. So let's look at the first 1 GPU case. And if you look at that, then the P40 is actually better than the RTX 3090 in terms of price per token generation per second. So if you want to get the best value for your money, basically, this is saying that the P40 is better than the RTX 3090. So objectively speaking, I'll debate that as we get to the next chart as to whether it's worth buying or not. But the results show that from a pure price to token per second standpoint, the P40 is better than the the RTX 3090 and the P100 in single GPU cases. Now, if we go back and we look at 2 GPUs, it's obviously not the case. And in fact, we actually see a significant performance improvement across the RTX 3090. And again, this is probably due to the NVLink that's set up. At least that's my hypothesis anyway. So, that could be another reason, is the fact that we are using a different interconnect technology here, and that's what is driving this larger performance increase on the 2 GPU case. But to summarize here, guys, I just wanted to show you that, yeah, the RTX 3090 is the best. That's kind of obvious, but this is designed also to put numbers to it. So, if you want to know how much token generation can you actually get from the 3090, this is a pretty good place to start. And then we'll look at specific cases and particular models in the next part of this video. And then also, what is the best use of your money? Is another thing that I always try to keep in mind, because that's something that's important to me. I always want to know, I have limited resources and limited capital, so I want to know how best to use those as well. All right, so now let's look at a little more granular approach. And so I wanted to do 3 more analyses. There we go. So I wanted to look at things model-wise. So basically, from a tokens per second standpoint, each model, and then, each GPU, and then the other cases, so CPU and all, and then the models. So okay, next, I wanted to look at prompts. So for example, what I want to see is, is prompt difficulty, does it actually have an impact on token generation or tokens per second? And then finally, does the hardware environment, or where these computations are actually being run, does that have an impact on the load duration, prompt evaluation duration, and then the response evaluation duration? So the time it actually takes to do this processing. Does the hardware environment impact that a lot? So we'll start here with the model-wise analysis. And before we do anything, let me take out this ratio here, because we don't need that. That's something I just included for the next analysis later, just to make things easier to see. And the first thing, before we get too much more into this analysis, what I want to do is I want to pause, and I want to talk about this black line, because this is very important. This black line is, to me, what I would consider when a model is usable. And what I mean is, from a tokens per second standpoint, is the model, the GPU model combination on the hardware that it's running on, is it slow enough, or fast enough rather, that you can actually use it in production without wanting to rip your hair out? So that's, I did a lot of testing, and I was like, okay, well, how can we say, a GPU is worth buying, or a GPU and model combination is worth actually buying and using? Where do you draw a line in the sand, I guess, is what I was trying to figure out. So the idea I came to, and actually I love this, I found a tokens per second visualizer. I was actually going to build one, but I did some looking, and somebody had actually posted this on Reddit, and I found it. But basically what this does is you just enter a speed, and this shows you what the prompt generation looks like. So for example, the reason why I have the benchmark set at 10 is because this is what 10 looks like. And I consider this to be probably as slow as I'm comfortable going. I mean, it's still actually objectively kind of slow, but this is kind of where I drew my line. I was like, okay, if I can get a system to run 10 tokens a second for an LLM, then I'm comfortable with that. I'm happy with that, because you can actually, for small things, and especially, you could actually have a chat almost in real time for something like this. And of course, I'll link this website in the video description, because I think this is great. Okay, so that's 10. Let's refresh the page here, and just to give you, I think 80 was the maximum that we had today. Maybe 90. Maybe 90 was the maximum. So we'll say 90. But that's what 90 looks like. So that's extremely fast, and that's probably what you would find. That's more close to what you would find on ChatGPT, or some of the paid services. This is closer to the actual generation that you would find there. So, okay, and then by comparison, if we look at 5 tokens a second, this is, and some people, you might argue that this is doable. And while I think this is probably fine, this is, to me, you're going below the threshold where this is actually conversational. This is no longer what I would consider real time enough to be able to have a conversation. This would have to be something that you could use, or maybe build into an API that you're not actively communicating with via a GUI, or you're building an application. This may be something where you could build that in, or where this would be relevant at maybe 5 tokens a second. Still be slow. Probably have to adjust timeouts and things for large responses, but it would be doable as long as it doesn't need to happen in real time. So anyway, I just wanted to explain why I was drawing my lines there, and why I think that 10 tokens a second is kind of a tangible lower bound, shall we say, to what is usable for GPUs. So in terms of testing with that bound, what we see is, let me exclude this model as well for consistency. There we go. Okay, just to keep everything consistent, because we took the outlier out of the last one. I'll take it out here as well. So what we're seeing here is the RTX 3090 in all models that we tested it, or in all cases that it was tested, performed at or above our minimum requirement. So this is a check to me if you want to run it on any of these models. So basically anything that fits on its fully on its RAM, either in the its VRAM, either in the single or double GPU case, I think it's totally fine to run, and you can use it for like conversational applications. Where you probably get a better bang for your buck with the P40 is if you're going to basically use it as a single GPU, and you are going to run basically up to the full 8 billion instruct Llama model. So that's kind of where I would draw the line there. If that's what your goal is and that's all you need, then I think then this is probably a better buy, to be honest with you. And then, as we can see here in the CPU case, none of the CPU cases I tested were, at least on average, the CPU didn't do well enough to even make a recommendation for using the CPU. So I was kind of disappointed. I was hoping to see better performance out of Llama, to be honest. I was hoping that it would make it realistic to just use the CPU. And I think in some cases you still probably can, if you, like I said, you want to use the API applications, or you're not needing it for real-time chat interfacing. I think it'll probably be fine. Excuse me. And then the all scenario is pretty bad. I mean, it kind of starts where this ends almost, and in most cases, it's also going to fall behind as well. So if you are going to have a lot of GPUs and you want it to be performant, then you're probably going to need to go with something with high bandwidth, like the 3090, or something a little bit more robust than the P40 and P100 and stuff like that, because you just get and again, this is like a mismatch of all of the things, and there were cases where I ran it on I ran things that were too big, like in this case where you get almost negligible, like zero performance. So that drags the overall average down quite a bit. But for all those other models, it's still not good enough to actually really run like I think that you would want. So in any case, guys, that's the analysis here, and then you can dig into it more deeply if you'd like. Like you could select only one GPU or 2 GPUs, and I didn't not all the tests overlap because I didn't want to waste my time, and some of the times I couldn't go to the next model without fitting it onto the using the CPU as well. So I tried to just test the models where it made sense, but unfortunately that means that there are gaps where things don't overlap quite as well. So there is that. Let's see. Yeah, I think that pretty much covers this one. So let's move on now to prompt analysis. Here, what I was expecting to see actually is I was expecting to see, as the prompts increase in difficulty, I was expecting to see kind of like a slight upward trend here. But really, you don't really see much of anything. So this is tokens per second, by the way, and then this in this blue chart here is the total duration or average total duration for each of the prompts. And so what you see is while each prompt on average takes more or less time to actually get through, which is basically attributed to the fact of like how many tokens are being generated. So by a pure token generation standpoint, this is the most complex, and it has a slightly. I don't think that's the lowest. Let's see, that's 18.7, and that's 18.75. Okay, so yeah, this is actually the lowest. The lowest case, but just because the most tokens are generated here and it takes the longest, doesn't necessarily mean that there is a one-to-one or linear decrease in tokens per second versus the like second longest case. So what I'm trying to say is that it doesn't look like the prompt really has much to do with the token generation. Like it maybe is a kind of a fine, makes a very small impact. And maybe that's just because the prompts I tested really weren't that representative of all the different cases there could be. So, I think from a prompt analysis standpoint, you could probably do a lot more here and go a lot more in depth. But, just for the sake of the study and keeping things kind of short, like I would say that overall prompt is not something that really impacts tokens a second all that much, at least according to these results. The next thing or the last thing I did is I looked at things from a hardware standpoint, and I wanted to understand, okay, does the hardware environment actually play a role in the like time it takes to actually generate these responses? And if so, where is most of the time spent? And that was really kind of what I wanted to find out most. And it doesn't really look like, there's not really a lot of information to find out which hardware environment is better. It doesn't really look like there's much difference in relative terms. So this is just percent, of the total time. So, from a relative perspective, there's really not. From a hardware perspective, there's really not much difference in all of these. But the one thing is overwhelming is the fact that the majority of the time is spent in response evaluation or generating the response. The loading is negligible, and then the prompt evaluation in a lot of cases is also pretty much negligible. And in fact, let's see, what's the prompt evaluation is 8.2%, and this is 0.23. And this one I can't even get my cursor on, honestly. Okay, 0.27. Okay, and this is 0.23. Oh, sorry, 0.29 prompt evaluation. Yeah, 0.23. But anyway, these are almost the exact same. I just thought maybe one would be a little better than the other, but they're so small, it's almost pretty much negligible. So anyway, the load is literally zero, comparatively speaking, and then the prompt evaluation is almost negligible compared to the response. So that's the overall summary that I would say there is the important takeaway is that your time is being spent in response generation, and the hardware, it's kind of hardware agnostic, it doesn't really matter, and the hardware doesn't really make that much of a difference in terms of that. All right. Last thing here, guys, is I wanted to do a model cost versus quality, or I guess quality versus cost, I should say. And like I said, I used two different publicly available metrics here to do this. So I was trying to get a hard metric as to how good is this model, and then what are you paying for that goodness, basically. So I used the Open LLM leaderboard, which you can find here, and I'll link these in the video description. But basically what this does is it has a bunch of benchmarks that it runs and then takes the average. So you can kind of apples to apples compare these different models in kind of a academic way almost. So I took basically this average here, and that's what this number is here. So for the 8 billion half precision, and then the 7 billion instruct half precision, those are the only ones that are actually listed or that I could find in the leaderboard. So that's why they're the only two here. Which is fine. This will give us a kind of a quick, easy way to compare. And then the other thing is I use this chatbot arena LLM leaderboard. And so what this does is this actually allows you to, like the community, to look at two different models, give them the same prompt, and then choose which one actually performs better. And then I took this arena score. So that's what I'm using as a way to benchmark. Okay, we have an academic from the Hugging Face, but how, in practice, how much better is one versus the other, and how noticeable is that to the average person? And then, so arena score is a little bit convoluted, but this kind of tells you how that works. And, it may not be the best for an apples to apples comparison like this. It probably is better just to generate a ranking. But I think for the purposes of this study, I think it should be fine. But basically it looks at how this is actually done. And I think it's an ELO score that quantifies LLM performance. It uses the ELO rating system. And then it's also a BT. I don't want to spend too much time on this because it's really not that relevant. But in any case, if you're curious how this is calculated, it's here, and they have a link to the paper in the here, so you can go to the paper as well if you want. I just didn't personally have time to actually go and read it, but if you want, it's 29 pages, so if you want, you can go through and read it. I just didn't have time. So anyway, just wanted to show you, if you're curious about the score, how it came to be. You could check it out. But for the purpose of our study, we're going to directly compare it, even though it's wrong. Like, it may not be scaled correctly for this kind of comparison, but we're going to do it anyway. Just wanted to acknowledge that in case anybody was also thinking that. So, but let me explain this, what we're trying to get at here. So, what I did is I wanted to say, okay, here we have these ways to assess model quality in terms of the Hugging Face score and in terms of the LM Arena chatbot score. And then what is the minimum cost that would actually cost us to run this? So AKA, let's buy a GPU that we can use to put this on. So in the 8 billion, in this case, this is one singular P40 is what this comes out to be. And you could probably use the P100 if you really wanted to, but I don't know that it would fit all the way onto the GPU because it's exactly 16 gigs and the GPU itself has exactly 16 gigs as well. But hey, you could try it and it might be a little bit cheaper, but I just chose the one that I knew would work. And then also I did the same thing here, and I chose, this is the equivalent of 6. I think it's 6 P40s that will actually work. Yeah, sorry, I just did the calculation, but it's 6 P40s that will actually, it's the bare minimum you would need to be able to run this. So that'll cost you about $2,000 to be able to run this model. So anyway, this is minimum cost to run. And then the next thing is the scores. So that's the Hugging Face score for the 8 billion and then for 70 billion, and then the LLM Arena score for 70 billion and 8 billion. And then these are cost adjusted, basically. So how much are you paying for one increment increase in score? So in this case, you're paying $24 for a 1 point increase in this Hugging Face score. And in this case, you're going to pay 48. And then similarly here, for a 1 point increase in the LM Arena score, how much are you paying? And you're paying 29 cents here, and you're paying $1.61 here. So anyway, this is important, or what I'm getting at here is these ratios. So just from a minimum cost to run perspective, you're going to pay 6 times more to run the 70 billion instruct model than you would if you just stuck with the 8 billion. So for paying 6 times more, what are you actually getting in terms of quality? So if we look here and we look at the cost per Hugging Face score, or basically cost per score, I guess we should look at all this. So if you look at the actual score itself, you're getting basically 3 times the quality in terms of academic benchmarking from Hugging Face with the 70 billion instruct versus the 8 billion. So okay, so basically you're paying 6 times, but only getting 3 times the quality. So maybe that's worth it. It depends on your use case, depends on what you're trying to do or what you need, what level of quality you actually need. So is that 6 times increase worth the 3 times increase in quality that you're actually getting, if that benchmark is in fact indicative of quality? And then the next thing that's interesting is from a ratio standpoint, like how much does it actually cost you, or how much so this is how much you're actually paying for one point, one score point, basically, and then the same thing here. So how much more expensive is one score point from one model to this model? So this is actually twice as expensive. So it's twice as expensive. Sorry, so basically what this boils down to, a better way to say it, is the quality here, this is 7 billion quality, is twice as expensive overall as what this one is. And you could have probably done the same thing, just divided these two ratios, and it would pretty much give you this as well. So, and it boils down to this: you're paying 6 times the price for something you're only getting 3 times the benefit of. So my point is, whenever you don't need a level of, like, the cost that you pay is exponential for the quality, for the amount of VRAM, for the computing power. You're always going to pay a lot more than, it doesn't scale linearly. You're always going to pay a lot more, almost exponentially, for minor gains, is what I'm trying to get at here. And you can see that again, actually probably even exacerbated for this LLM score. So basically, there's almost a negligible difference between, people are actually, like, the score that people are giving the 8 billion model and then the score that people are giving the 70 billion model. So what that says is that in terms of what people can actually tell, or how people actually use this, the 8 billion is almost just as good as the 70 billion. So in this sense, you're actually paying 6 times. So you're paying 6 times for a 1.06 increase in model quality in terms of what people actually feel when they're using it. So, and this is the basically that ratio. So you're basically paying 5.64 more times more for the same quality, essentially, is what this actually means. So this is just a metric to kind of compare apples to apples in terms of quality. And what this is saying is that you're paying twice as much for quality in terms of the academic benchmark, and you're paying almost 6 times as much for quality in terms of what people actually, or the kind of benefit that you actually get tangibly. So at least based on the chat arena benchmark. So anyway, my point, guys, is I'm not trying to dissuade people from picking one GPU versus the other GPU. What I am saying is I think people a lot of times get enamored with the new models, the better performance, this, all these other things that's new and shiny and bright, and you forget that there's a cost associated with all of these things, and the newest and biggest and fastest is not always necessarily better when you factor in cost. Of course, cost aside, it's always better. You always want the best performance, but when you start factoring in cost, you have to, there will always be trade-offs. And that's why part of the reason why I started this channel is because I think it's so important to always keep costs in mind when you're making these kind of decisions, because, A, resources are limited, and B, it really depends on your use cases. And if you are smart about the way that you choose things, you can maximize your money and get the most benefit for whatever project it is that you're trying to pursue. So anyway, guys, that's it's a wrap up for this. I know it's already been really long, and I'm sorry, I've been trying to keep my videos shorter, but sometimes there's just a lot of information. And today, that was one of those days where there's a lot to present, And, I'll try to make it as digestible as possible in the description so you can jump around and you don't have to listen to me drone on and on about stuff that you don't want to hear. But anyway, guys, I really, really appreciate it. I hope that you enjoyed this video as much as I did making it. And I will see you in the next one.
All right, guys, brief reminder here. If you enjoyed the content, please consider giving me a like and a subscribe so I can continue to grow and produce better and better content for you. If you really enjoyed the content, you might even consider buying me a coffee, and the link for how to do that will be in the video description below. If nothing else, please just give me some feedback in the comments and let me know how I'm doing, if anything's unclear or if there's anything that I can improve on. Thank you again, guys, and have a great rest of your day. Bye-bye.